Okay, let's get started. This lecture is about chapter 9 of our textbook. Chapter 9 is a key chapter in moving forward towards the applications of stochastic dynamic programming. After the completion of the chapters on measure theory and integration, and the other is on Markov processes, we are ready to add stochastic shocks to dynamic optimization problems, dynamic programming problems. This is done in chapter 9. The whole chapter is directed at two formulations of stochastic dynamic problems. These problems are related. They are different, but these problems can be formulated in two related ways. One is quite specific. The first one is quite specific, and the other is quite general. The chapter is very, very long, so here we can only focus on the first formulation. Here I will show you both formulations, but we will focus only on the first one. You can see the two Bellman equations in the slide. You can see the two Bellman equations of the two problems. The first Bellman equation belongs to the basic neoclassical growth model, its stochastic version. You can see the Bellman equation looks quite similar to the deterministic formulation. The only exception is that we have a stochastic shock to the production function. So parameter z is a stochastic noise that affects the production function, and you can see that the second part of the right hand side of the equation is formalized with respect to the expected value of the value function. So in this first case, the shock is known. Period t shock is known when in the same period the economic agent is supposed to make its decision, his or her decision. So most importantly, the agent can choose the endogenous state variable for the next period. You can see y stands for the value of the endogenous state variable next period, and the economic agent can choose the value. The other formulation is different because the timing of the shock is different. We have an example in the textbook. So for instance, it's a storehouse, and we want to choose the value of a stock for next period, but there is a stochastic shock to the stored quantity. So you can see in the right hand side of the second equation, even if the economic agent can choose y for next period, this is not the state for the next period, because the endogenous state variable next period is also affected by the shock next period. So the timing of the shock is different from the previous case. Even if the economic agent can choose a value for y, which is supposed to be the endogenous state variable next period, the economic agent altogether cannot choose the state for next period, because it is also affected by z prime, the exogenous shock variable next period. Most attention in the chapter, is paid to the first formulation. So this is what we are going to do. You can find the explication of the second formulation in the textbook. So the agenda for this lecture is very simple. you may remember we covered the deterministic case in chapter 4. So we will try to go in line with chapter 4 to see how adding stochastic shocks to dynamic optimization problem affects the basic theorems of chapter 4. First, we need to clarify how can we ensure how we can ensure that the solution to the sequential problem and the solution to the Bellman equation exactly coincide, both in terms of optimum policy and the functions, the value function. So this is what we are going to do first, and then we proceed in line with chapter 4. We will ensure the strict concavity of the value function. We will ensure the differentiability of the value function. So we will examine the key assumptions underlying these qualities of the value function. Let's do this. Let's start with the principle of optimality. Just like in deterministic dynamic programming, the principle of optimality is about how to ensure that solutions to the sequential problem exactly coincide with solutions to the Bellman equation. We can formalize the same problem, dynamic optimization problem, in a sequential form or in a Bellman equation, and we want the solutions to both formulations to be the same. And the principle of optimality describes the basic assumptions that we need to ensure that these solutions coincide. So, okay, first the notations. We have two measurable spaces. One is for the endogenous state affected by the decisions of the agent, and the other is for the exogenous state, the shock, and they have a product space which is easy to understand if we have the basic neoclassical growth model as an example. In that model, we have a single endogenous state variable, capital stock, and we have a single exogenous state, the shock to the production function. And in this case, the state of the system can always be represented as a point in a plane. The point has two coordinates. One describes the endogenous state, the other describes the exogenous state. This is about representation. We have a transition function Q defined to describe transition dynamics. These transition dynamics are supposed to be stationary, so irrespective of the time, transition function Q assigns the same transition probabilities to the exogenous state, irrespective of the time. And we have a correspondence. It's very important. I wouldn't say it's more important than the other part, but this is very important. Okay, so we have a correspondence which is a set-valued function, and such a correspondence, just like in the case of deterministic dynamic programming, describes the set of feasible choices in terms of the state of the system. So a correspondence in every period describes the available choices. Its graph is A, which consists of points with three coordinates x, y, z, and this is the reason why we will use this graph, because you can see that one period return function f has A as its domain, because f has three variables x, y, z, and these variables come from the graph of the feasibility set from the correspondence. And Last but not least, we have a discount factor with which the agent calculates the value of the plans of her actions. So plans, this is the keyword for the later discussions. What does it take for us to solve a dynamic programming problem? Uh, we have an initial state consisting of the endogenous and exogenous state, and the decision maker, in our understanding, the decision maker forms so-called contingency plans. What is a contingency plans? It's a key term, it's a key thing, so I think it's worthwhile for us to slow down and talk a bit about contingency plans. In deterministic case, when we have okay, let's have the deterministic formulation of the basic neoclassical growth model. In this case, we have an initial state, which is an endogenous state, but in this case, it makes no sense to distinguish between endogenous and exogenous states. So we have a state variable, capital stock, and the economic agent can form plans, courses of actions, with which we can describe system dynamics. So if we have a policy function that assigns endogenous state variable next period to endogenous state variable this period, given a plan and given an initial state, we can describe system dynamics. If we have multiple plans, we have multiple system dynamics, and given the one period return function, we can calculate the value of such plans, and we can compare the values of such plans, and we can choose the plan that gives the highest satisfaction, the highest value to the agent. In broad terms, this is what we did in deterministic dynamic programming. In stochastic dynamic programming, we would like to do the same, but we cannot, because system is also affected by an exogenous shock to which the agent wants to respond. So in advance, the agent cannot form a course of action. Her best bet is to form contingency plans, to form functions with which she can respond to exogenous changes in the environment. So a contingency plan is a series of measurable functions with which the agent responds to exogenous changes in the environment. Practically, we hope to have a single valued policy function, but you can see that in the stochastic case, such a policy function has two variables, one of which is the exogenous state. So we assume agent to respond to the exogenous shock, the evolution of the exogenous state variable. So what is a plan? A plan is a series or sequence of measurable functions with which the agent responds to changes in the environment. Because we discriminate between endogenous and exogenous state, and the endogenous state is under the control of the agent, everything is about describing how the agent responds to the exogenous state, to the shock. Soon you will see what it takes, what it means to describe the actions of the agent in terms of the shock history. I will show you a very simple example. most importantly, a plan must be feasible. So in every period, the plan that practically is a value for the endogenous state variable next period. So practically, a plan must always be feasible through time. So in every single period, the agent is supposed to pick a value for the endogenous state which is available to her. So this is the reason why we use the correspondence, because once again a plan must be feasible. In every period the plan must the value she chooses, she plans to choose for the endogenous state next period must be in the feasible set. And here comes the first assumption, assumption 9.1. Gamma is non-empty, its graph A is measurable, and gamma has a measurable selection as a function h. This function is key because if we have a feasibility set with multiple available choices, this function as a measurable selection can be a plan. So a plan, we describe the plan as a function that responds as inputs that responds to the actual state of the system. If the endogenous and exogenous states move in Borel sets, then theorem 7.6 ensures that there is a measurable selection. So from the feasible set, once again, for more emphasis, the feasible set gives feasible choices in every period, and a plan, an alternative plan, is no more than a selection, a function from this feasibility set. I'd like to show you what it means that plans can be described in terms of shock history. Let's choose a very basic but very instructive example. We have a policy function in this form. You can see this is a linear policy function with which the agent can respond to the state, including the endogenous and exogenous state variables. So we have this policy function, and we can describe the first choice with the policy function, and we can use the recursive structure of this problem to realize that, so this is the initial state, and we can realize that recursivity works. So here we can put the previous endogenous state into the policy function, and finally we will have this equation. And you can see something interesting. This is the initial value of the endogenous state, for instance, the initial value for the capital stock, and here we have a role for the shock history. Let's go ahead. The third action is this, according to the policy function. And just like in the previous period, we can put x2 into the policy function. Yes. And expanding this equation, yep. The same. So the initial endogenous state and shock history. Let's take one more step before generalizing the results. We will do the same. We will put the previous line into the policy function. And it equals to, this is the final row we are doing, I promise. Because here we have a setting which can be generalized into a recursive formula. So if we did the same, finally we would receive this formulation. So this is the constant term. This is the initial value for the endogenous state, and this is shock history, from 0 to t. And that's all. So this is the general formulation of the for the endogenous state. You can see we have an initial value for the endogenous state. This is shock history. So everything depends on the shock history. Given that the agent responds to the shock, the system evolves according to the exogenous shock. So this is the reason why we can use this recursive structure of the problem, and this is the reason why we can describe the evolution of the endogenous state as the function of the exogenous state, because okay, we have the evolution of the exogenous state, and this equation describes the evolution, the dynamics of the endogenous state. So given the fact that the agent controls the endogenous state, and given that the agent wants to respond to changes, exogenous changes in the environment, and given that the agent forms contingency plans, by which we mean that the agent forms functions through which she can respond to the environment. Dynamics of the endogenous state is the function of the dynamics of the exogenous state. That's all to it. Let's go back to the plans, the problem of plans, candidate plans, for a split second. What does it mean that the agent has candidate plans, possible plans? We saw that the correspondence gamma describes the set of feasible values in every period in terms of the state, the endogenous and exogenous state, and the agent is supposed to pick a value for the endogenous state next period from this feasibility set. So in every period there is a feasible set from which the agent picks one value for the endogenous state next period t plus 1. If we order these possible choices into sequences, then we have plans. So this is the sense in which we talk about candidate plans. The agent is supposed to find the optimum plan. And by optimum, we mean the plan that gives the highest satisfaction, happiness, or whatever to the agent. So the agent is supposed to find the plan that gives her the highest satisfaction value. So to find the optimum plan, the agent is supposed to compare these plans, and this can easily be done by calculating the values of these candidate plans, compare these values, and most easily to go for the most valuable, the plan with the highest possible value. The problem is still the same. These values are expected values because the system is exposed to stochastic shocks, and these shocks are unknown in advance. But the probability distribution is known because we have the transition function q. So we can calculate the expected value by defining the probability measure mu t as defined in section 8.2, which describes the probability of a stochastic shock going through a measurable rectangle of whatever dimension. So assumption 9.2 is about giving the basic characteristics of the one-period return function that ensure that the value of a candidate plan could be calculated. You can see under assumption 9.2 that the value is the discounted sum of the one-period return functions in the subsequent periods. Let's stop for a minute. When an agent follows a plan, it means that she chooses values for the endogenous state next period according to the plan. So in every period, by following the plan, in every period the state of the system can be described by three coordinates, x, y, and z, and these coordinates can be put into the one period return function. So by following a plan, the situation of the agent can be described in every single period, can be described by the one period return function in that period. The value of a plan followed by the agent is exactly the discounted sum of the one period return functions in each period. So we calculate the expected value of the plan by adding up the expected value of the one period return function in the future. Assumption 9.2 is about the basic characteristics of the one period return function, which it must have in order that this evaluation could be done. Okay, so the limit in one way or another, this limit under assumption 9.2 must exist. Okay, how can we measure the value of a candidate plan? We can calculate partial plans, the value of partial plans. You can see we can calculate the value of the initial state. We can calculate the value, this is un, we can calculate the partial value of a plan into the future of a given length, and the value of the whole plan is the limit of these partial plans. So when n goes to infinity, we goes to the value of the whole plan, this infinite plan. Under assumption 9.1 and 2, this function u, utility function, so the value for the function by which we evaluate the value of the plan, this function u is well defined on the set of the feasible plans, and on this set of feasible plans it's easy to interpret the supremum function. So given that we have candidate plans, given that we have feasible plans, we can find the plan or plans, it depends. So we can find plans that attains the supremum in the sequential problem. So plainly put, of the set, in the set of feasible plans, we can find a plan or plans that gives the highest possible value to the agent, and this is the plan that the agent is supposed to pick that gives her the supremum of value. If f takes on both signs, assumption 9.3 introduces a bound by which we can calculate. Taking a detour, we can calculate the expected value of a plan. So we have three assumptions, 9.1, 2, and 3. These assumptions describe the basic characteristics of the one period return function, of which the existence of the limit and integrability are the most important. So the next step is to solve the problem from the Bellman equation. Let's take the next step. Previously we were talking about plans that the agent picks from the feasibility set, the correspondence gamma. However, we can say more about these candidate plans. Let's have this Bellman equation. This is the stochastic version of the Bellman equation. When we solve the supremum problem underlying this Bellman equation, we necessarily have a policy correspondence G that consists of those y values that attain the supremum in the Bellman equation. So simply put, the policy correspondence G contains those values of y that are optimal. So the next step in forming plans is to pick plans from this policy correspondence, because by picking plans from this policy correspondence, we ensure that the plans are feasible, but they are optimal at the same time. So we are one step closer to finding the optimum plans. Here, this is just a reminder to chapter 4. Here we had, at this point in chapter 4, we had theorems 4.2 through 4.5. These theorems ensured that solutions to the Bellman equation and solutions to the sequential problem coincide, both in terms of policy and the value function. Here, measurability is a concern because the solution to the sequential problem may not be measurable. And if the value function of the sequential problem is not measurable, then it's not integrable. So this value function cannot be used in the Bellman equation. Simply put, because we cannot use this value function in calculating the expected value with integration. So honestly, we have less than we had in chapter 4. The key theorems in chapter 9 are theorem 9.2 and 9.4. These two theorems are related. If, according to theorem 9.2, if V is a solution to the Bellman equation, and this limit holds, and G is, as the policy correspondence is non-empty, then the value function as the solution to the Bellman equation is the same as the value function of the sequential problem. And the optimum plan from the Bellman equation attains the supremum in the sequential problem. So, most importantly, the plan generated by G, so the plan coming from the policy correspondence G, is optimal. Theorem 9.4 is the reverse of the previous theorem. We saw that the plan generated by G is optimal. The reverse is a plan is optimal if generated by G. Formally put, under assumption 9.1, 2, and 3, if a plan attains the supremum in the sequential problem, then there is a plan generated by G belonging, where G, the policy correspondence, belongs to the Bellman equation, so that the two plans coincide. So under assumption 9.1, 2, and 3, it is possible, it is very important, it is possible to find the optimum plan from the Bellman equation, and the two plans will coincide. Now let's turn to the case of bounded return functions. We studied the same Bellman equation, but now the one-period return function is supposed to be bounded and continuous. Previously, in the previous section of the lecture and the book, we studied the principle of optimality. We were looking for assumptions under which we could ensure that solutions to the Bellman equation and the sequential problem exactly coincide. We did so under very general conditions, but now we have some strict assumptions regarding the one-period return function, namely the return function is bounded and continuous. And now we are looking for assumptions under which the assumptions of the previous section still hold, so we can have the same theorems ensuring the coincidence of the solutions. So let's go. The first two assumptions are related to the state space. Assumption 9.4 is related to the space of the endogenous state variable. It is supposed to be a convex Borel set with all the Borel subsets in the sigma algebra. Z is the space for the exogenous state variable. Z is countable, so this is the case when the shock variable takes on discrete values. It must have a sigma algebra with all of the subsets, or in the other case, when the exogenous state variable is a continuous variable, that it is supposed to be a compact Borel set. Practically, it is a closed interval with all the Borel subsets in the sigma algebra, and the transition function Q has the Feller property. Just as a kind reminder, the Feller property is a property of the transition function. When we calculate the expected value of a function f with integration with respect to the probability measure q, the transition function q, then the function f may have some basic characteristics like continuity or boundedness, and if transition function q has the Feller property, the expected value of the function still has the same properties. So if function f of which we calculate the expected value is bounded and continuous, if q has the Feller property, the expected value of the function is also bounded and continuous. It also holds for monotonicity and concavity. If function f is increasing or strictly increasing, then the expected value of the function is also increasing or strictly increasing. And if the function is concave, the expected value of the function is also concave. Let's have further assumptions. Correspondence gamma is non-empty, compact valued and continuous, and the return function is bounded and continuous, and the discount factor lies between 0 and 1. We will see soon that in exercise 9.6 that under these assumptions 9.4, 5, 6 and 7, the previous assumptions still hold, so we can still have the same theorems as we did in the principle, in the section, the principle of optimality. So under these new assumptions, it is still true that the solutions to the Bellman equation and the sequential problem coincide. This is a great achievement. Let's take the next step. We have the Bellman operator as the stochastic version of the Bellman operator we used in chapter 4. Simply put, this is about value function iteration. According to the next theorem, theorem 6.9, under these assumptions, the Bellman operator has a unique fixed point. So by iterating on the value function, we have the hope to reach the solution V of the problem as a fixed point, and this fixed point is bounded and continuous. The policy correspondence is non-empty, compact valued, and upper hemi-continuous. The next two assumptions about the return, one of them is about return function f, which is supposed to be strictly increasing in x. The notation, about the notation, you can say that I use the same notation as Stokes and Lucas used in the book. AYZ is the YZ section. YZ section. We use this notation first in chapter 7, I guess, when we were talking about the x and y section of a set. This is the same but in 3 dimensions. So A, Y, Z is the YZ section of the graph A of the correspondence gamma. Correspondence gamma is very important in every problem because correspondence gamma and its graph A describe the relevant points relevant to the problem. So the correspondence describes the feasible sets for every pair, every XZ pair, and hence the graph A is a shape in 3 dimensions. The YZ section of graph A contains the relevant values for the variable x. So we don't say that f is strictly increasing in x in general. We say f is increasing over those x values which are relevant to the problem. So without digging too deep in this notation, please memorize, please understand that graph A describes, it contains the relevant points for the problem. Okay, so this is the reason why f is supposed to be strictly increasing in the relevant x values. Gamma is increasing in the sense that if x prime is higher than or equal to x, then the correspondence, the feasibility set belonging to x prime, the correspondence gamma belonging to x is a subset of the correspondence gamma belonging to x prime given z. And the last theorem for the slide, under these assumptions, fixed point v, the solution of the Bellman equation, the value function iteration, is strictly increasing in the first variable. The first exercise of the day is exercise 9.6. What we need to show is assumptions, under assumptions 9.4 through 9.7, we have the earlier assumptions ranging from 9.1 through 9.3. So let's go over the assumptions one by one. According to assumption 9.1, correspondence gamma is non-empty and its graph A is measurable. So this is the first thing we want to check. Graph A is, this is just a reminder, graph A is a set of 3-dimension points with coordinates x, y, z, so that y is in the feasibility set. So this is the definition of graph A of the correspondence. So A is a shape, is a 3-dimension shape. The circumstance that graph A is measurable, it means, so measurability means that graph A is in the related sigma algebra. So this is what we want to demonstrate. This is what we want to show. I have a figure which shows the discrete case when the stochastic variable z takes on distinct discrete values. So let's define the following sets. Let's define the following sets. These sets consist of points with two coordinates, supposing that y is in the related correspondence. So it's a very simple graph. So I try to show you these two-dimension shapes in the three-dimension space. So according to assumption 9.6, for every zi, gamma is non-empty. This comes from assumption 9.6. So these sets are measurable. Let's take the next step. Let's define these sets. For distinct i's, and in this case the graph A is the union of these shapes. These AI sets are measurable. So their finite union is also measurable. Hence, their finite union is also measurable. Okay. Note that measurability comes from the fact that we work with Borel sets and Borel subsets. A part of assumption 9.1 is the existence of a measurable selection in gamma. Here we need to refer to theorem 7.6. We need to check if the prerequisites of theorem 7.6 hold or not. So, what are the prerequisites? Gamma is non-empty. Yes. Assumption because of assumption 9.6. Gamma is compact valued. Yes. Assumption because of assumption 9.6. And gamma upper hemi-continuous. Yes. According to 9.6, gamma is continuous, so it is also upper hemi-continuous. Because the prerequisites of theorem 7.6 hold, there is a measurable selection, so altogether assumption 9.1 holds. This is our first result. Okay, let's proceed to assumption 9.2. Assumption 9.2 is about the measurability of the one period return function f. F is continuous. F is continuous with respect to the Borel sets. See exercise 7.10. So f is a measurable because of the three variables of the one period return function of x, y, z. Assumption 9.7 sets the continuity and boundedness of one period return function f. So f is mu t integrable. So this part of assumption 9.2 holds. See Bartol's book, page 41. And another consequence of the fact that f is bounded, that the limit under assumption 9.2 exists. So just like in exercise 9.2, we can build on the limit. So assumption 9.2 holds. Okay, this is the second result. Okay, and last but not least, assumption 9.3, f is bounded. So there is a series of functions in this form where b is the bound of the function f. So it is easy to find a series of functions Lt, which is equal to the bound of the one period return function. So we can call into play assumption 9.3. We have the appropriate bound. So assumption 9.3 also holds, and we are done. More unbounded returns. We have further assumptions to ensure some basic characteristics of the value function. These characteristics are familiar to us. These are the same characteristics we were working with in chapter 4. First of all, we have two further assumptions. One, assumption 9.10, is about the concavity of f, the one period return function in the usual sense. And assumption 9.11 is about the convexity of gamma, the correspondence, the feasibility set. Under these assumptions, according to theorem 9.8, fixed point v of the Bellman operator, under these assumptions, especially assumption 9.10 and 11, value function is strictly concave. Concavity is a very common characteristic of the value function. We like if the value function is concave because concavity is in line with the basic idea of diminishing marginal returns. So this is the reason why we really want the value function to be strictly concave. The next theorem, theorem 9.9, says that under the same assumptions, we can find the optimum policy function while iterating on the value function. So while we are iterating with the Bellman operator on the value function, we have approximate policy functions, and these approximate policy functions converge to the optimum policy function. And last but not least, sometimes, most of the time, we need the differentiability of the value function. It works very similarly to the material in chapter 4. So this is the case of the Benveniste-Sheinkman theorem. We can gain the partial derivatives of the value function with the partial derivatives of the one period return function. The idea is the same. We need a function which in a point is equal to the value function, while the value function is higher in other points. So the idea is the very same as we had in chapter 4. The next case is the case of unbounded returns. Previously, we were dealing with return functions which were bounded and continuous. Now we have return functions which are unbounded. According to theorem 9.2, value function v, the solution to the Bellman equation, must abide by a limit restriction. So there is a limit restriction on the value function for all possible plans and all initial values. There is a problem here. If the return function, one period return function, is unbounded, there may be initial points and there may be plans for which the limit doesn't hold. In this case, we have a way out. We define a restricted set of plans, and this restricted set as a subset of the set of all plans. This restricted set of plans consists of plans for which the limit holds. And then, if we have this restricted set of plans, we can define the supremum function, so we can find an optimum plan on this restricted set that optimizes the value function. On this ground, we get to the next theorem, theorem 9.12. If V is a measurable solution to the Bellman equation, and the related policy correspondence G is non-empty, and if, this is the serious part, if we have an optimum plan in the policy correspondence, and if this plan, this is the most important part, if this optimum plan is in the restricted set of plans for all for all values, and if there is a plan in the restricted set that dominates any other plan, including the plans from the unrestricted set, then the solution to the Bellman equation is equal to the solution of the sequential problem. Okay, so practically we define a restricted set of plan. On this restricted set, we find an optimum plan, and under these crucial assumptions, the solution to the Bellman equation and the solution to the sequential problem will be the same. So actually and practically, theorem 9.12 has two basic assumptions. We need to check these assumptions in empirical work, not empirical, theoretical work, or both. We need to check if these two assumptions underlying the theorem hold. One of the assumptions, checking the first assumption is easy. We need to check if the limit restriction holds. The other assumption, the dominance assumption, checking of the dominance assumptions may be more difficult. The strategy is quite common. We can show that any plan is in the restricted set. So if we find a plan in the restricted set, which is the basic idea of the theorem, so if every single plan, every possible plan is in the restricted set, then the optimum plan dominates any other plan. Or we can show, in the other case, we can show that we have a plan in the restricted set for which the limit restriction holds, and we can show that any other for any other plan, the value is minus infinity. And in this case, 2, the optimum plan from the restricted set dominates any other plan.